So, what did you do in your year off for COVID, Jono?
What? Aside from making money, mostly little musical projects, some online stuff, and lots of breaking lockdown to rehearse in my mate's basement. In the end, there was only one band I'm in that didn't rehearse in person last year, and that's because it's our MO.
Your MO?
Yeah, modus operandi. The whole premise is that we never rehearse. In fact, we've never played a gig either, for that matter, and we absolutely never will. Playing music, it's so much the antithesis of the band that we joined on the basis of what we can't play rather than what we can. And that means I'm one of the few guitarists currently in the lineup. But couldn't even string together 3 chords in the truth if I had to. Oh, can't even remember who started the band.
So, what's the point?
Same as any band, isn't it? To be famous, or perhaps notorious, or maybe even both. Anyway, anytime anyone asks, we just say we have creative projects in the works. Expect something big. Any day now.
So, what are you called?
We're called Grunge Cutter. You know, the thing in the DE's courses. It's a pretty apt name. Never used it. Couldn't use it if we tried. Yet, sounds cool. And, despite its uselessness, it's famous anyway. Pretty much what we aspire to.
So, it's a bit like Spinal Tap then.
Maybe they're an inspiration, maybe not. But at least we'll get the dimensions right on our Stonehenge. The advantage of never having played a note, though, is that no one can pin you to a style. Anyway, I better get back to studying for mechanics, Kev.
Alright, Jono. The course is fun?
Yeah, everyone loves grunge, but it becomes pretty legendary once you get into Hamiltonian mechanics. And those Poisson brackets? So 80s hairband, if you know what I mean. Today's background is a scenery shot from a fairly well-known tourist district in Tokyo. It's Nakamise Street in Asakusa, which is just behind a fairly famous attraction called Kaminarimon. Most of you will have seen photos of it if you've seen anything from Japan. It's a big red gate with a big red lantern hanging underneath it, and then the 2 sides of the gate are these 2 demonic creatures. And you walk through underneath this gate, and there's a big shopping district of souvenir shops running behind it. That's all the red buildings that you can see along here. And if you slip out one of the side alleys from that souvenir shopping district, there's a whole pile of shops flanking off to either side. Lots of shops for various things and a lot of restaurants. And a lot of people wander around that district in the day, mostly because that's when all the tourist shops are open, that you can see here. But it's actually an interesting place to go at night because there's quite a lot of good restaurants and you can get some really good food there. It's also a really nice place to get some good night photography shots if you're into photography as well, which is why this is one of my sort of favorite photos and favorite places to go wandering around getting photographs in Tokyo. In this second half of the lecture, what I want to do is step back from doing Hamiltonian problems because there's one last piece that I want to pick up specific to Hamiltonian mechanics, and that's the idea of Poisson brackets. So let me bring up some slides. What we want to do here is go back to being algebraic again, and I want to step back from the Hamiltonian slightly at first to consider a general function of the phase space F. Okay, so you'll remember from the last lecture, what we had was we have a number of coordinates for our system, 2n coordinates in this particular case. Half of them will be positions, half of them will be momenta, and we create this space out of it. And for our system, at any particular point in time, we can specify a point in that multi-dimensional space that tells us what the values of all of those coordinates are. And then as the system evolves as a function of time, those various coordinates will change, both in terms of position and momentums, and they will follow some trajectory through that space. Okay, and as we saw on the in the last half of the lecture, if you have a simple harmonic oscillator, it will basically just follow an ellipse in that phase space that corresponds to the motion going backwards and forwards as a function of time. Okay, we can connect all sorts of functions to these sorts of trajectories, and what we're going to do here is just start with some general functions so that we can look at the concept of Poisson brackets, and then we'll build Hamiltonians back into them a little bit further down. So we're going to do some algebra. We're going to need some paper, and where I want to start here is by looking at the rate of change of our function f with respect to time. And so what we have is our derivative of df with respect to time, having the following form that we know from several variable calculus. It's going to be I equals 1 to n of df on dqi, dqi on dt, plus df on dpi, dpi on dt, plus df on dt. Okay, and so this is just this idea that we used in the last lecture when we were dealing with a Hamiltonian, and we're all familiar with from when we just deal with total derivatives in x and y. You take the total derivative and it's some component of the derivative with partial derivative with respect to x and a partial derivative with respect to y. And here all we're doing is generalizing that to a multi-dimensional space. Okay, same idea that we had in the last lecture, except we're doing it with a general function f and not just the Hamiltonian for reasons you'll see in a second. So what we can do is do the same step that we did last time of dealing with the time derivatives. So sum from I equals 1 to n of df on dqi, this becomes qi dot, plus df on dpi, pi dot, plus df on dt. Okay, so the next step here is that we can basically bring in Hamilton's equations that we had from earlier in this lecture and the last lecture. So these two things are qi dot is equal to dh on dpi, and pi dot is equal to minus dh on dqi, like so. Okay. And what we can do is substitute those in for the qi dot and the pi dot in the line above. So let's do that. What we're going to have here is sum I equals 1 to n of df on dqi. Our qi dot will give us dh on dpi, plus df on dpi times pi dot, which is minus dh on dqi. So what we need to do is kill that plus sign there and make it a minus, and this will be dh on dqi, plus df on dt as the last term. Okay, so the thing you'll notice here is that my change from just a Hamiltonian to a phase space function f is somewhat deliberate, because I don't want to go down the same path that I did in the last lecture. You'll remember when we did this in the last lecture, we got dh on dqi times dh on dpi minus dh on dpi times dh on dqi. Those two terms are the same. You subtract them, they get 0, and all you're left with is the partial derivative of the Hamiltonian with respect to time. I don't want to go back there because we end up with 0 and the problem goes away. What I'm doing here is introducing this phase function f so that I can set it off against my Hamiltonian H here. And I'm going to do that deliberately because what I want to do is have a look at this first piece of this derivative here as a thing that we call a Poisson bracket. And so what we're going to do here is step back even one more step further. We ripped out the Hamiltonian in the first place and put in a phase space function f. What we're going to do now is rip out the Hamiltonian again and replace it with another phase space function. And this one we're going to call g, right? And so what we can do is define a thing called a Poisson bracket. And this is nothing more really than a mathematical convenience. Is a way of taking the term there that's got a bunch of derivatives and a sum at the front and writing it as something a little more simpler. Okay, so what this thing will look like is curly bracket f g curly bracket is equal to sum n I equals 1 of df on dqi dg on dpi minus df on dpi dg on dqi. Okay, and so you notice there's a nice symmetry there. So on the left-hand side, we got F and P. We've got on the left-hand side, we've got F and Q and G and P. And on the right-hand side, we've got F and P and G and Q. And we got something that's nice and stable, but sometimes under certain circumstances might actually drop out to 0. Okay, so this is our Poisson bracket that you can see here. And it's a thing that we use quite a lot. If you go on to do a lot of Hamiltonian mechanics, you'll see this thing pop up again and again and again. It's a really nice, useful thing to have. What we can do is take our equation that we had up above, and now that we have this concept of Poisson bracket, we can write it in a really simple form. So what we can do is write df on d, and I should write the right d here just to be precise. D on dt is just equal to the Poisson bracket f and h plus df on dt. Okay, and this thing here, we'll number it number 2. This thing is sometimes called Hamilton's equation, and the thing that you find sort of weird after a while if you do classical mechanics is there's all sorts of things all over the place that are called Hamilton's equation. And the funny thing about this is that this version of Hamilton's equation, we'll see in a minute, will actually pop out the other 2 Hamilton's equations that we've dealt with earlier on. And so this is sort of why they're all sort of got the same name of Hamilton's equations, because they've got the same original origin, and it just depends which one you want to use. Okay. The interesting thing in here is if our phase space function has no explicit time dependence. So if f is independent of t, then df on dt is equal to 0, and df on dt is just equal to this really simple thing, this Poisson bracket f and h. Okay, really nice and an elegant little solution in here. So it looks like just a little bit of mathematical play trickery in here until we get to the point where we start to put something in here. And I'm going to put 2 phase space functions in. I'm going to put one of them as P of I and one of them as Q of I, and we'll see some interesting things pop out. Okay, so let's look at, we'll call it case A here. We're going to let F be equal to P of I. What we'll get here then is dP of I on dt is equal to our Poisson bracket P of I and H plus dpi on dt. And of course, this term on the end here is equal to 0, and it's equal to 0 because the pi has no explicit time dependence in the problem that we deal with here. It's a coordinate. Okay, so what we can do is go through here and write pi dot is equal to sum I equals 1 actually what we'll do just to disentangle our I from the elements in the sum is we'll just make this j. So j equals 1. This will be now dpi on dqj dh on dpj minus dpi on dpj dh on dqj. Okay, so I've just in my Poisson bracket, all I've done is just change the referencing from I to j to make sure that it doesn't clash with the I that I'm using for my pi here.
we've got this thing. We know that we know two things. We know dpi on dqj is equal to 0 always. And this is always going to be the case because pi has no explicit dependence on qj. Okay, the easiest way to think about this is you've got a 2n dimensional space, and one of the axes is pi and the other one is q, and they're independent coordinates in this system, right? There's no dependence between the two. Our dpi on dpj is going to be equal to basically the Kronecker delta of I and j. So it will be equal to 0 if I is not equal to j, and it will be equal to 1 if I is equal to j in here, okay? And so if we play this through, what we'll get is pi dot is equal to the first term on the left here, first term on the left here gets killed by this derivative being 0. The second term on the right here survives. So what that does is it means that the minus sign that is sitting in the middle here turns up as this minus sign just here. And we keep our sum, j equals 1 to n, of delta ij dh on dqj. And of course, the Kronecker delta there in the sum will knock out all of the terms except for the one where I is equal to j. So this thing very easily pops out to be minus dh on dqi. All right, you'll be familiar with this. This is just one of the two Hamilton's equations that we had earlier, right? We can follow the same line of logic here in case B, where we basically make f equal to qi. And if we do this, it's interesting, random change of pen color, then what we'll have is dqi on dt is equal to our Poisson bracket, qi and h, plus dqi on dt. And of course, for the same reasons in here, this thing will be equal to 0 as well. It's a coordinate on its own. The system might have some functional dependence on time, like you know, the Lagrangian or the Hamiltonian, but you know, the coordinates axes for the systems are not going to change with time, otherwise you're going to run into problems in here, okay? So that's going to be 0, and so what we're left with is just dqi on dt entirely comes from the Poisson bracket. This thing ends up being qi dot is equal to sum j equals 1 to n of dqi on dqj dh on dpj minus dqi on dpj dh on dqj, like so. And then likewise, we have dqi on dpj is equal to 0 always. And our dqi on dqj will be equal to our Kronecker delta of I and j in here. And so we can take this one step further. Our qi dot will be equal to sum j equals 1 to n of delta ij dh on dpj. So what we've had in this particular case is that this term survives and this term dies as 0, okay, and it takes the minus sign with it. And so the Kronecker delta in here will only be 1 when I is equal to j. And since we're doing the sum, all the other terms have zeros, so we're left with one term, which is going to be dH on dPi. And so this is our other Hamilton's equation that we get out here. Okay, so let's just summarize this real quick. Our case A, F is equal to P of I, gives Pi dot equal to Pi and H. Our case B, where we put in F equals Qi, will give us Qi dot is equal to our Poisson bracket of Qi and H. And then these, of course, pop out. Pi dot is minus dH on dQi. And Qi dot is equal to dH on dPi. Okay, so there's two things I want to go back and note real quick before we move on to sort of the kicker at the final piece of this discussion. And that is that we have to be a little bit careful about what we mean about partial derivatives in respect to this argument. So you'll notice in here, I've done a couple of things in here where I've gone partial derivative of Qi with respect to t is 0, partial derivative of Pi with respect to t is 0, and so forth. Some of you will be going, well, hang on a second, isn't it possible for the momentum to have some dependence on time? After all, I mean, if you consider over time, the momentum may change, and likewise for dq on dt. You'll notice in here that the derivative of p with respect to time turns up twice. It turns up once in this term on the end, and it turns up again in this term at the front. And those two terms, those two derivatives, are two very different things. The derivative at the end, which is the partial derivative of pi with respect to time, what you're really asking there is, does pi itself as a sort of a coordinate axis have some explicit dependence on time? And if you think about this in terms of your phase space, what you're really saying is your phase space stretching as a function of time or contracting as a function of time, or is it fixed? And you would like it to be fixed, right? Because otherwise it's going to be really hard to deal with. You can imagine, you sit in the lab and draw a graph and ask whether your X and Y axes are fixed as a function of time. And you'd hope they are, because otherwise things are going to be rather hard to work with, right? So what we're saying here with our dp on dt here, the partial derivative being equal to 0 is simply that we've got a coordinate system that's not really changing as a function of time. And so the only place really where we have partial derivatives changing as a function of time is if we have functions of the coordinates and the function is changing as a function of time. That will be the case where you get those partial derivatives not 0, but the partial derivatives of the coordinates themselves with respect to time will always be 0 in all of these problems. If you think about the other derivative, the total derivative of the coordinates with respect to time, that's where you get into these ideas of, for example, can the momentum or can the position change as a function of time? Yeah, of course it can, but it will change because of the dynamics of the system and not because of a change in the actual coordinate system, right? And if you consider this equation that you've got here, the dp on dt with the d, not the partial sign, is not 0. It's got a dependence on the Poisson bracket between the momentum itself and the Hamiltonian. And of course, the Hamiltonian is the function of, and it's a function of all of the coordinates and time that determines how the energy behaves, right? And so as long as that Poisson bracket is not 0, then momentum or the coordinate or whatever is corresponding to it can change as a function of time, but it will change because the system is changing and not because we're changing the coordinate space in that system, okay? And so this is where you have to be very clear about the difference between the partial derivative with respect to time and the total derivative with respect to time in terms of the argument I just made, okay? The other thing that's kind of rather significant in here is that the Hamiltonian always seems to turn up in all of these Poisson brackets. And the main reason for that is that the thing in your physical system that determines how that physical system evolves as a function of time is the Hamiltonian, right? It's the thing that tells you how the energy behaves as a function of all the positional coordinates, all of the momentum coordinates, and time as well. And since it is the key to the evolution of the system, it's going to turn up in all of these Poisson brackets that we have in here for all of these other phase space functions. And the phase space functions are really things that just depend on some aspect of the phase space, okay? When we're thinking about Qi and Pi in this particular case, we're really thinking about replacing the f in this function here with the corresponding Qi or Pi. And of course, all of the other components that would be in that functional form will all disappear, except for the one that's connected to the thing we put at the front. So really what we've got is Qi, Q1 is just going to be a function of one thing, which will be Q1, which is kind of just trivially saying it's a variable. P6 might be just a function of P6 on its own. And when we take, for example, this partial derivative here, all we're really saying is that it's got this variable has no dependence on time, and it has no dependence on any of the other variables as well. So that's why when we get up into these arguments up in here, for example, where we say that, certain derivatives are zero always, and the Kronecker delta knocks out all but the one where I is equal to J, what we're really saying is if we put Q3 at the front, the only thing that can be a function of is itself, because it's just trivially a variable, and all the other ones drop out. And that's why all of the other derivatives are zero, except for the one that has the same index label of the same type, okay? Really important key to understanding the logic of how this all goes together, because it's just, whenever I teach this, it's a really common question, but hang on a second, how can this work, okay? All right, so that sort of brings us to the end of defining our Poisson brackets, but what I want to do is point out very quickly some notable mathematical properties that we have for Poisson brackets. And the first one is a bit of a giveaway, but I'll work through all three. So the first one is anti-symmetry. And what I mean by this is that if we take the Poisson bracket of F and G, and my squiggly brackets often get a bit curly, if I just have a squiggle on the page, you know what I mean, it will be equal to minus G and F, right? So if we reverse the order of the two functions in a Poisson bracket, we'll get a minus sign popping out the front. And you can see that in here. If you go through and just do the maths with this particular definition for the Poisson bracket, and go through and reverse the order of these two things, you'll find that what you get is the negative of the thing that if you hadn't reversed them. Okay, I'll let you prove this one for yourself. It's actually pretty easy to do. Bilinearity is the second. So these things behave in a really nice linear fashion. So for example, if you had lambda f plus mu g and h, what you would get in here is lambda of f and h plus mu of g and h. Okay, so these things behave in a really linear fashion for lambda and mu scalars. Okay, so they're linear. And then the last thing is they obey something known as the Jacobi identity. F, G and H plus G, H and F plus H, F and G is equal to 0. Okay, and you can demonstrate this for yourself. It's essentially tied to the first property of antisymmetry. But what you're doing here is working around a circular argument in terms of your things in here. Now, if you look at these three things, and you've ever done a quantum mechanics course before, you go, hang on a second, this looks just exactly the same as a commutator bracket, right? So if you're in quantum mechanics, you'll go, well, you know, there's this thing that we call a commutator bracket for two operators A and B. And this thing's really just A, B minus B, A. And the first thing that you do in a quantum mechanics course is demonstrate that the commutator bracket obeys antisymmetry. In other words, if you reverse the two operators, you get a minus sign. The next thing you do is you demonstrate that this thing is properly linear. And bilinearity is nothing more than demonstrating that it's linear in terms of the prefactors and linear in terms of the sums. And then a common problem to do in quantum mechanics, often you don't do it in the lectures, you might do it as, you know, the tutorial problem. Sometimes it gets thrown out in an exam, and I've thrown out an exam in the past because it's kind of a fun thing to do. You'll prove the Jacobi identity as well for commutator brackets. And so if you're switched on, you'll notice that commutator brackets have exactly the same mathematical properties as Poisson brackets. And in particular in quantum mechanics, if you work your way through, you start to look at the time evolution of an operator A. And it can be any operator you like. It can be a momentum, it can be a position, it can be a Hamiltonian, it can be all sorts of things in here. And what you find is a thing called quantum Hamilton's equation that basically looks a little bit like this. The time derivative of the operator is equal to minus I on H bar, A H as a commutator plus dA on dt, or sometimes you see it actually in its version with expectation values. So you'll see it looking something like d expectation value of A on dt is equal to minus I on H bar expectation value of the commutator plus the expectation value of the partial derivative of the operator with respect to time, like so. Okay, and this is a thing called quantum Hamilton's equation, and you can see that it has a very direct correspondence to what we see here in classical mechanics in our Hamilton's equation. All we're really doing in going from quantum mechanics to the classical limit is taking our commutator A and H and replacing it with I H bar Poisson bracket of A and H, where A just corresponds to our operator A hat. Okay, and the interesting thing that you'll notice in here is that whether it's our classical mechanics Hamilton's equation or our quantum Hamilton's equation, the Hamiltonian is sitting in there, and the Hamiltonian is sitting in there in both cases for the same reason. It's the function that tells you about the way the system behaves as a function of its coordinates and time connected to the energy behavior of that system. Okay, so this is probably the best place to leave off Hamiltonian mechanics, but it's a really nice place to point out just the parallels between classical mechanics and quantum mechanics and see that, you know, there's connections directly between these two. Essentially what you have in quantum mechanics is you just take your classical Hamiltonian mechanics and extend it into the quantum regime, and you get matching equations, and then those things obey what we call the correspondence principle, which is the idea that when you take a quantum mechanical system and drive it back towards a classical limit, it should return to its corresponding classical equation, and that corresponding classical equation will be your classical Hamilton's equation that we just obtained in this lecture. Okay, so this is a good place to finish. The next two lectures will be on damped and forced oscillators, and I'll see you next time.